Alright guys, the file IO in Node.js. So in this particular lecture, we're going to discuss the file operations in Node.js, and I'm interested specifically in how Node.js does the synchronous versus asynchronous file reads and writes. You see, file operations are expensive because you're talking to an external entity. When I say external, it's not doesn't mean external disk, but an external to hardware, right? Outside the OS, and that there is a communication cost. The hardware has a cost. There's a lot of data structures in the hardware itself, whether it's SSD or disk drive. And I have a detailed 3 lectures or so in my operating system course. I encourage you to watch that to know the intricacies inside that device. But there's a cost to it. And as far as we know, this operation is always synchronous, i.e. when you call a read or you call a write, there is a cost to it. And the Linux and Windows and operating systems in general don't have a asynchronous approach to reading files, unlike network. There's no epoll for files, right? So when you make the read call, whatever thread made that call is blocked, and you have to understand that, and you have to work with what you have, right? Now, IO reorg is the exception, but not really, because we're asking the kernel to make the blocking call in that particular case, right? It is very similar to what we're doing here. I'm gonna show in a minute. But we're gonna make a call. If you're a thread that made a read to a file, you'll be blocked for whoever that period of duration until that read is completed, right? Now the OS makes our life easier and has a file cache on top. It's called a page cache, disk cache sometimes, that when you issue a read, it goes directly to the cache and returned, right? If you issue a write, it's a write through cache, so they write to the cache and then asynchronously at some time they write to disk, right? So there is a page cache that significantly improve the performance, which sometimes databases disable for one reason or another, consistency and, funny enough, performance reasons. If you have your own cache, why do you need the OS cache? Does that make sense? But it's a little bit of a complicated topic, and it's one of the topics that people take PhDs in, just file systems and how to read from file. It's absolutely interesting. So take this as just a step to move forward to understand how file systems work and file IO in general. And let's start with the first one, read file. Read file is an abstraction created by Node, well, that doesn't exist in reality, right? And what that does, it opens the file, which is it has its own meaning, opening a file, i.e. take the path and convert that path, look it up into the file system, find where it is, find if it even exists or not, and give me the metadata for that file. When was it created? Who created it? How big is the file? When was it last modified? All the metadata. And the most important metadata, where does it live in disk? Which LBAs does it live in? And the LBA is basically the block, the starting block that tells you this is where the file begins, right? And you can start asking the disk, say, hey, read me this LBA, the logical block address block, and it will just give you that. Then you can read the next one and the next one and the next one, right? There's like the file system tells you this layout. But that's what read file does. It opens the file and then it reads the entirety of the file, the entire file. So watch out, always watch out. When you're issuing a read file and you don't know how big the file is, you might get into performance issues and in some cases failures, because read file cannot read like more than 2 gigs, I think. And then after it does, it closes the file. In certain situations, it actually may keep the file open, and I couldn't get into when it does that, but it seems to be in certain some heuristics, like if the file has been opened a lot recently, it keeps it open just in case you might need it again, right? So sometimes it keeps it open for performance reasons, right? And there is a cost here, you guys, right? And I always, in my courses, I always emphasize the cost of opening, of the cost of everything, right? And every time in my courses, I always emphasizes the costs of doing things. And there is a cost to opening and closing and path resolving. And in fact, there was a recent optimization done by the Node.js team to switch from constantly using paths to file descriptors, which is what you get when you open a file, which is what you get when you open a socket, which is what you get when you listen to a socket, which is what you get when you bind, which is what you get when you accept a connection. You see, with Linux, everything is a file, right? It's just a number, and it's easier to deal with integers, right? And files are not different. If you open a file, you get back a file descriptor that points for that particular process, for that particular file. This is the number that matches this guy. So you can see naturally, if you're dealing with paths, and if you pass, like if you have a function that opens the same file over and over and over and over again, and you're always passing strings, you're incurring the cost of resolving that string, right? First copying that string because of memory operation, then resolving it to do a lookup in the file system only to find that it exists, and then read the metadata again, and then it creates a file descriptor. And maybe you're gonna search for open files and then map it to existing open files. So there is a cost, right? So you can avoid that if you want to, by not using paths all the time. Of course, if you're just opening it once and you know what you're doing, then that's fine. But yeah, read file in itself is asynchronous. There is a version of it that's called read file sync that is, you guessed it, it's synchronous. So let's talk about these guys. So the read file sync is executes right there and then. Whenever you called it, wherever you called it, it will execute. So it will execute in pretty much any phase that you call it from. It can execute in the poll phase, it can execute in the initial phase, it can execute in the close callback phase, any phase. And the reason is because it's synchronous. And because it executes in any phases, it's executed in what we call the main thread. We didn't talk about threads yet, right? We kind of talked about it when we discussed libuv, right? But there will be a dedicated lecture for threads. But that main thread is what executes most of our stuff, the callbacks. Most of the time, this is what we execute stuff. So when we do read sync, we're telling Node, hey, I want you to now read the file right now. Don't delay it, right now. And I'm gonna wait right here until you're completely read the file. And then once you do that, return the content of the file to me, and then unblock me, right? So it's a completely synchronous call. You do this, then you do the read, and then you move on, right? So you'll be blocking the main thread in this particular case. So yeah, so this also happened in the initial phase. So watch out if you're doing a lot of these in the initial phase. It might slow down node startup, and as a result, it might slow down the event loop. And if the event loop slows down, what will happen? Well, things that were supposed to happen in the poll phase won't happen until later. So your listening sockets might not be there. Your other read operation might not happen. Your connections might not be established. A lot of things can happen when you delay it, right? And of course, once the read is done, the data is returned. So that's how it works. It's always done on the main thread. Take the other approach, which is the asynchronous approach, which moves the burden of the blocking to one of the UV threads, and just say, hey, and I'm gonna read the file and call me when you're ready. And this is, we're doing a callback, right? So I'm calling read file, and you give it a callback. When the read is completed, call this callback. That's what it means. We are still blocking, but the blocking is happening in this thread, which we don't feel it. The main thread can resume normally. It resumes its event loop, unlike here, right? If I'm doing the loop, I am blocked here. I cannot resume the loop. I cannot resume. Oh, sorry, I'm covering that thing. But yeah, I'll just draw it again here. Yeah, unlike the event loop, I'm blocking the loop here. So if I'm in the timer phase and I do a read file sync, the timer phase will block the execution until read file sync is complete, and then I'm gonna move to the next of the phases, right? Well, here I can just boom. I just move on with my loop, right? I just schedule a read, and I schedule it to run in the poll phase, right? It says, hey, I want to do a read. I says, sure. I'm going to do two things, right? When we schedule something, schedule the actual execution of the read and schedule a callback. And the callback by default, it's not ready until the read is ready, right? The read is complete. So this is what happened. We execute this in the libuv thread, and all of this is done magically by Node.js. And it's essentially just say, hey, you can do it yourself if you want, right? Spin a thread and then execute a read on that thread, right? And so you can simulate exactly how read file work by spinning a thread and calling read file sync on that thread. And then whenever it's ready, it will communicate back the result. So we're just playing tricks here, right? That's what we're doing. We're just playing tricks. Whoever is being blocked just changed. That's the only difference. And the main thread, the most important thing is like you don't want to block the main thread because there are timers here. There are close callback. There is pending callbacks. There is idle prepare stuff that needs to happen. You don't want to block that, right? You don't want to block that. So that's, and we're going to talk more about this in the performance section. I never block. Avoid blocking this main thread, this pretty thing. Keep it running. Keep it just going. And sometimes you cannot help it because there is always execution happen here, right? But sometimes like this, you can, like read file sync. It's okay to call read file sync, like reading certificates when you first start up. Starts the HTTPS server. You need to read the private key and the certificate so you can spin up an HTTPS server, right? So yeah, you can read files synchronously because it's tiny, and well, I need it to read it, to communicate. And you can say, no, I'm actually gonna read it asynchronously on the poll phase, and when that happens, I'm gonna have a callback that actually sets up the listener. You can do both. And we kind of talked about this. And we kind of talked about this, the UV thread pool. By default, it's 4. threads, and you can increase it. So watch out when you do a lot of asynchronous read files, and also if you're doing DNS, even if you don't know about it, right? Just doing request or Axios, HTTPS, example.com, that behind the scene does a DNS, which uses one of these guys, right? Read file uses one of these guys. So if you're doing a lot of them, and all of them are queued in this poll phase, you might fill them up, right? And then new guys, new read files will get queued, waiting for these puppies to free up. It's fascinating once you understand things. I don't need to tell you anything. Once you understand things, you'll just say, okay, I understand that. And that's it. When you run into it, you at least you know, right? It's like I'm telling you that fire burns. That's it. That's the only knowledge I give you. I'm not telling you, oh, if you see a fire, run away, or maybe you enjoy fire. I don't know what you want to do, right? So, well, to give you the knowledge, then it's in the back of your head. It's a useful knowledge. Now you can use it, you can avoid it, you can do whatever you want with it. But now you're aware, and understanding in this life is what matters. Just understanding the state of things. That's to me at least. Let's throw an example. Let's go ahead and throw an example. So I'm recording an FS here, and I'm just printing a bunch of messages here. So what I'm going to do is start the initial phase and print about to read the sync. I'm going to read a sync, do a synchronous read here. And I'm just going to read the same file name that I'm running. It's just convenient to read the same file name, but you can only do this if you do require. I wish they do it in import. It's just so silly that they don't. And I understand maybe it's a cost. It's not a cost. I know the file name. I know it's my file. I don't know. Yeah, it's just one of my pet peeves. And then what is this thing? UTF-8. So UTF-8 is an encoding. You see, when you read a file, by default you get back a binary. Ones and zeros, and these you get it as a buffer, and more specifically just an integer 8, I think, just an array of bytes. Literally, that's what you get. Now, array of bytes might not be useful for you if you have, let's say, a Japanese text which is written in kanji. You don't want the kanji for shin to be whatever bytes it is. You don't care, right? The above the bytes, you want the actual kanji, right? Or if it's an Arabic character, you want the actual Arabic character, right? You don't want the bytes behind the Arabic character, whatever they might be, right? I suppose decimal can be, you can talk through decimals better, right? It's like there is a byte has a decimal value. We don't care about that. So UTF-8 is the encoding that changes, it scans the bytes and parses them and convert them to UTF-8 encoding, which is what we understand as a human and can read. So if it sees like 4 bytes next to each other, this is the kanji of forever, right? And then it will show you in the screen that kanji. So one character can be 4 bytes, right? And yeah, one letter could be 2 bytes, things like that, right? And you can go into what UTF-8, but what I'm getting at is this is not free. Good job. Nothing is free in life. Nothing is free. This is the most thing you're gonna hear from me. Nothing is free. Everything has a cost. If you want to convert it to UTF-8, then there is a cost to it. Just understand it. It's like, Hussein, what do I do with this now? Or is there a way to eliminate the cost? You cannot eliminate anything, right? first understand it, and if you want to eliminate it, that's a different question, right? It's like you might, because you might be okay with that cost. You might amortize. Amort, I'm looking for a word. I can't pronounce it. Amortize, to spread evenly, right? To spread the cost evenly. Amortize. I forgot what the word is, but you know what I'm talking about. So yeah, you wanna spread this cost. You wanna do it at the beginning, right? But yeah, UTF-8. Then I'm reading it synchronously, and I'm doing the UTF-8 synchronously. Everything is synchronously, so there's a cost to all of this thing. Right? You might know that, hey, I'm reading ASCII, so ASCII is a little bit cheaper to parse compared to UTF-8. Yeah, as long as you know that you're reading an ASCII file. Finished reading file sync file, then you just print the messages, and then we're doing another one read file, but this one is synchronous, and I'm also want to UTF-8 it. And then we're just doing callback here. This is the call this when you're ready, and also schedule this in the poll phase. This guy executed in the initial phase. This guy, no, is gonna execute in the poll phase. And then we do a timer, and then when the timer is elapsed, do all these print messages, and happen to also do synchronous read in the timer. So this sync read will be executed in the timer phase. This sync read will be executed in the initial phase, and this read will be executed in the poll phase. Right? So technically, and again, it depends who wins, because this is like a 1 millisecond. So maybe this is first and then followed by the rest. And then I'm also doing an asynchronous read in the timer. So I'm just playing games here to see what the output is. And it turns out to be, this is the initial phase. In the initial phase, we read the file synchronously. That's the result. And we read the file synchronously, finished reading the file synchronously, about to read file async, about. Just the about of them, right? And then finished. Well, really didn't finish, did we? We just scheduled it. I should change the wording here, but you know what I mean. And then we start the timer phase, and then we're about to do a sync read. We finished. We schedule an async read, which goes to the poll phase, and then I want to see the one did we no, there is a result of the async read, result of the async read. Here is the result of the async read. We get it right after all the timers, and from timer, result of the async read. All right, so this is the first output, right, at the end, and this guy, this callback, the comes later, results from the timer one. And you can see it's a game of the event loop being executed with different stages. Let's talk about file descriptors. To avoid opening and closing the file, you can open the file and get a number. Yes, Node.js exposes this for you, right? And you can issue a read by using that number. So if you're planning to read and reset the read multiple times from the same file, you don't really need to read file, read file, read file, read file. Let's say the file is changing constantly. You can just open it for read, and of course, someone can change that file, and you can read those changes as you go, right? Provided that you didn't lock the file while reading. So this is just a shared read, and of course changes can happen while you're reading, as long as you're not opening an exclusive lock on the file to prevent writing, right? It's much faster and avoids the path lookup, and even open and close have these versions of async and synchronous. You can open a file for synchronously and close a file synchronously, right? And you can use this read offset buffer. We're going to show an example actually. And of course, opening a file comes with flags. You can open the file for append, for read only, for synchronous mode, right? To skip the file cache. I never tried this. We're going to try this together now. Right, this is another mode, RS plus. But you can say, hey, I'm opening the file just for writing. I'm opening this file. So just read through these and then just keep them in the back of your head. You don't have to memorize them or anything. It's just, hey, know that they exist. Knowing things exist, sometimes they just pop back up when you absolutely need them. That, hey, I once read that. And will prove useful. Sometimes it might be completely useless and we'll never use it ever. Right? Most of us will read a file and will not change it. We'll just open it for read. Let's talk about file streams. Read files, as I talked about it, read file reads the entire file and puts the entire file in memory. So there's a problem here, right? Because if the file is too large, then you're gonna get this error, ERFS file too large, and that's the, I think it's greater than 2 GB, because this is the file that I attempted to open, I think a 7 gig file, and you get an error that says you get 2 GB. That's it. You cannot remove it to you. In that particular case, you use streams, which we're gonna have a dedicated lecture on. But essentially, streams are very useful to have a dedicated fixed size memory in Node that the source of the file pours in, and then you read from this chunk of memory. And then once you drain that chunk of memory, some other chunk comes from the file and fills its place. And you consume it, and you consume it, and you consume it slowly. So there is like 2 stages. It goes to memory, and then from memory to your stuff, and then it goes away, right? So you stream it, right? And you can do so much cool things with stream. Like you can create a stream and then you chain it to a write stream, which then you can chain it to a transformer stream, like a compressor. You can compress the file, encrypt it, and then write it back, all in 3 lines of code. But of course, there's so much happening behind the scene. We're going to show that in the stream lecture. It's a pretty cool feature. But just watch out, because streams are not free. There's something happening behind the scene. Okay, here's me trying to open the outline of this course, actually the backend course. And this is how you read it in a stream mode. So basically you do an event, and the event, what is happening behind the scene is we asynchronously call read, the same read that I showed here, right? Read, and when the read is successful, the node fires this event, say, hey, I have a chunk, I have a chunk, I have a chunk, here it is, I have a chunk, I have a chunk. And it will, you just, by listening to the data event, you can just get the chunks in a pace that node can handle, and whatever the chunk size, you can control that as well. And then when the stream ends, you're gonna fire the end event. You will get an end event, and you can control it. So we're gonna show that as well. Here's some gotchas, and I think you know this by now, but it doesn't hurt to repeat it. Read file, when you call read file, that when you get the callback for read file, that indicates the time the callback was executed, right? So when you call read file and say, hey, execute this when the file is done, that callback only executes when at the time of that execution of the callback. It does not indicate the time of the actual read, right? So because the actual read might have happened 5 seconds ago, and we scheduled the callback and we mark the callback as ready. Because remember, when we call a read file, we do two things. We schedule a read operation and we schedule a callback and we mark it not ready. When Node picks up the read execution operation and actually execute it, and when it's done, it goes and marks the callback as ready. It may or may not execute it right then or there. It depends on Node's mode. Like, okay, do I feel like execution this, or did I do too much in the poll phase? Let me just delay it until the next phase. Or sometimes it will execute it right there, but it will be marked as ready, because maybe when the read happens, that is expensive, right? We're gonna call the read, so we move on to the check phase and the other phases, and then when we come, by the time we came back, the node libuv already marked my thread, my callback as ready. So as I come back, it's now ready for execution. So there's a big difference between these two, right? So it's possible that the read has finished a while back, but the poll phase didn't pick it up, right? Because the callback was not ready. And let's do some demos. So we talked about node file IO, the synchronous and asynchronous version. We talked about threads, right? How libuv schedules a file read on one thread. Talked about streams a little bit, and let's do this. It's good exercise. I'm gonna do a trace, our friend. I'm gonna trace node file IO and see all these pretty examples. See what Node does behind the scenes. Let's get started. Let me view the first file, 440. And what we have is this. We explained this in the slides, right? We have a read file sync, reading UTF-8, and then we're printing this synchronously, and then we're gonna read this, and this is asynchronous. There's so much happening here, right? So let's just run it, and you can see that the schedule, we're doing so much right here, so it's not worth tracing that, right? I rather trace something simple. But if you run this, let's go ahead and run it. Node 14. You can see that we started initial phase, we read the file synchronously, we got the result, and I'm only printing the length because the file might be large, right? So I'm just printing the length of the file. If you finish the read file sync and then ended the initial phase, and we're just going through that. Now you can play with this file if you want, but I'm interested in the second one. It's actually more interesting. For one, this guy. Let's do this guy. This is interesting. I'm gonna stress this guy. Here, I'm doing an open sync, and I'm getting a file descriptor, and I'm printing that file descriptor, and I'm reading the file using the file descriptor as opposed to the file name. Okay, so let's keep that in mind, and then closing the file descriptor. And I'm gonna just play with these values because we have a bunch of them, right? We have append, AX, A+. We're reading this file name. So that would be dangerous to read this file name as right. So let's keep it read only and see what is going on. What's going to get. Let's do an strace. Strace dash T dash F forks. Because this is synchronous. Yeah, this is interesting. I'm going to do that. We're going to do one synchronous. This is all synchronous. Let's do that. Node. That's to be say node. All right, we got the output. That was quick. That was really quick. How about we actually print it to a disk or something, right? It's easier. It's a cleaner. Dash out. Dash O out the text. This is the output. We get a file descriptor 17, so that will help us look it up. So open, and you can do And you can see, we're going to see a lot of opens, by the way, guys, because Node just not only opens my file, it's going to open tons of other files. So let's just find one way to do it, I suppose, is just do equals 17, right? And that, no, that's not my file. That's not my file. There's a lot of stuff that starts with 17, I guess, huh? That looks like my file. Saying course 14 file sync. We read the file, and these are the, when I say are, these are what we get, what we send to the open operation. So let's read through these guys. So let's read through these guys. There is read only. So the read only flags is for read only. So what's the other one? There was another one, right? Enable the close on exclusive flag for the new file descriptor. Specifying this flag permits a program to avoid additional setfd operation. Note that the use of this flag is essential in some multi-thread program because using a separate fcnt operation to set the fd close exclusive flag does not suffice to avoid race conditions where one thread opens a file descriptor and attempts to set it to close on exec flag. Okay, so the gist of it is fd close on execute literally means after you execute it, close the file. That's what it means. Because I'm gonna re-execute this read and then just go ahead and close the file. So that's what it means. Hey, I'm just opening it, I'm gonna run few things and then just go ahead and close it. So feel free to close it. Okay, so this is my file. So let's change it a little bit. What I'm gonna change here, I'm gonna change the file. How about we play some games here? Let's change the file to something else. How about we do this? Let's change this. I want just to do the rs plus. Let's just do one. I want to see what do we send when I do rs plus, which is this guy, for reading in synchronous mode. I want to see what do we send. And let's just pray that this doesn't corrupt my file. Right now. Okay, let's go just look for my file. There you go. All we have to do is just do osync. That's the extra thing, and read on write, right? So now we have an extra osync that's being sent. So what is osync? You might say. Osync. Now osync, write operations on this file will complete according to the requirement of synchronized file I/O integrity completion, by contrast with the synchronized I/O data integrity. By the time write2 returns, the output data associated with the file metadata have been transferred to the underlying hardware. So to translate, what this means is this will sync. This is different than synchronous from Node perspective. This, as you write to this file, anything you write will be written to the cache and also will be written to the hardware, to the SSD itself, before it returns. Okay? So if I am writing something to this file, usually if I don't have this flag on the file, it will write to the cache, to the file system cache, which you don't know about, which is kind of invisible to us, and then it will return. It says, hey, I wrote it successfully, right? But if you do it with osync, that write will go all the way to the disk and then will come back. And that write will only unblock when we actually written to disk, right? And this is essentially equivalent to calling fsync, which I also talked about in my course. Like fsync is literally force the synchronization, i.e. whatever I have in this file descriptor in the cache, just flush it to disk, right? So that's basically what it is. Okay, what else do we have? Vim 14, we have 42, we have the file max. All right, you guys, so let's do this. This example, I have a large file here, the quick 0RTT video, and we're gonna read it multiple times. We're gonna play with the thread pool here a little bit. So what we're gonna do is we're gonna issue 100 reads, and then using promise.all, i.e. when all of them are done, I just want to say, hey, we read all of them successfully. And what do we do in the promise data? I'm just doing a promise, I'm promising this. I can't say that word. I'm turning this callback into a promise by returning a read file and do a callback. So this is all of these guys are asynchronous. And we're going to do an strace. Hopefully the file's not too large for us, but we're going to see that each read was done in a different thread, right? Compared to the synchronous one, which is done in the main thread. Okay, so we're just going to resolve that, hey, it took us this much to read the files, right? And we're going to play with we're going to change these parameters as we run them, okay? And actually, let's copy this because this is going to be useful. So let's run it with one thread and node, no, like that. So this is how you set an environment variable. UV thread pool size 1, just one thread. And then we're going to run this guy, and then we're going to get a failure because this file doesn't exist in my Linux file. So I need a large file. I created a large file. Apparently you can use this command, and it's going to be large.file pwd. So home saying large file. Let's go back. And then we need to print something that's just like, okay, at least say, hey, console.log start reading, something like that, right? And then 100 is a lot, dude. Let's just make it 10 at least, because this machine is not that great. Let's do that. Start reading. It's reading my file, and of course one thread is okay. I changed it to 4 so we don't have to wait forever, and it took 2 seconds to read with one thread. So let's try it with 4 thread, which was what this is what we have. I have 4 cores on this machine, and you can see it's slightly faster, of course, and it's not going to get any faster than that, but you can experiment that. The more thread you have, it depends on how many cores you have and how many executions are you getting right here. So let's do this. Actually, let's do 4, because we know 4 is faster than 1. 1 took 2 seconds, 4 took 700 milliseconds. But there's of course the scheduling time and the cost of all of this. But let's see what did we do. Let's do another 4. We got 600 milliseconds. That's nice. Now I'm gonna do an strace with 4. Okay. Dash T dash F dash F is very critical here. Dash O out.text. Ooh, does not like that I can provide. Maybe we gonna do this later then. That sucks. Can I do this set environment variable? I want to print the environment variables, right? Let's do this. Start reading with UV thread pool size process.env v Okay, we know it works. Okay, good. This works. How about this? If I do node, what's the default? Undefined. Right, so I'm gonna do it. UV thread pool size equal 4, and then do this. Still undefined. So actually you have to do export UV thread pool size between Windows, you guys, and other operating system. I can never remember the actual syntax, but you have to do export in Ubuntu. Okay, Ubuntu. So that's you how to do it. Okay, so we can do, now we have 4 threads. Now we can do my strace, right? And that will use 4 threads. And now finally I can do 4 threads of reads, and I can see what happened. File large.file. So I want you to pay attention to these files now that I'm reading. This is one read. It happens on thread 20386. 386. Another N. 388. So just like that, we have we read the file on thread 387 and another file on 388, and then we read it again on 390, and then on 389. So distinct 4 threads. Dun, 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 dun. Very good, right? So we read it on 387, then we read it on 388, and then we issued a read on 390 and 89. So they are distinct 4 threads. Okay, and we can play games with this. And now if I'm changing this guy, let's export to 1, and I do strace. Ooh, it's slower. Of course, right? Because now large.file, we read the file on 411, 411, 411, 411. It's all in the same thread. Now this is not the main thread, you guys, because the main thread is probably this one, 404. This is one of the libuv's thread pools. Okay, I love this stuff, you guys. Don't you like this stuff? And then of course, if you do it synchronously, how do we change this to be synchronous without breaking the entire? I don't think we can. Probably we can do it on what's the first file? That was synchronous, right? No, this first example was bad. It just has so much stuff to it. This one is good. This is synchronous. So let's do the strace and then do this one. I'll keep overriding the trace file, but it doesn't matter, I think. What am I reading? There you go. We're reading on the main thread. Now, how do I know this is main thread? Just trust me, bro. This is the main thread because we're reading other stuff on the same thread. 470. And you can see the distribution of threads as you start changing the game here. You can put more files, and you can see how many threads did we actually use, right? As you change those thread counts. I think this stuff is interesting. Okay. CD, what else do we have? I think that's pretty much it. That's the interesting things, at least. We had streams, and after streams, oh, the bypass cache. Okay, we did that. We did the bypass cache, right? The async, right? Remember? So that's how you read a large file. So let's go ahead and Hussein large dot file. This is how you read a large file. And then let's do node 1443. Ooh, and we read the entire file. So this is how you read the files using streaming, essentially. Right? So we read the file, and I'm just gonna include how to create a large file for you guys because I found it useful. Right? Large.file. This is useful because I just discovered how to do that. I think it's useful because we're gonna play with that a lot. So yeah, we read stream. We talked about it, right? We've opened the file, and then we listen to the data events. And as data come in, we have fixed length. And if we're lucky, you will see that the final read is always smaller, but the file happens to be so uniform that even the last one is actually the same chunk size. But yeah, guys, that's it for the file lecture, file IO. There's so much to explore here. There's so much to learn. And stress is your friend, especially like if you want to run something and you want to see where are the bottlenecks happening. Do you have enough threads to execute your thread pool? That stress tells you exactly like, hey, we had this much, but this is the number of threads that actually been used, right? So yeah, I guess see you on the next one, guys. I think the next one is DNS. The next one is HTTP. Take care.